In this video, we're going to follow up on the point group analysis that we had done previously on sulfur hexafluoride. And so if you want to go through the steps of determining what the symmetries are going to be of the sigma and pi salx on the fluorines, I recommend watching that video first, because what we're going to be doing now is we're actually going to then take that and develop the MO diagram for sulfur hexafluoride. So sulfur hexafluoride is a molecule that has OH symmetry. The sulfur will have the s orbital, which has A1G symmetry, and its 3p orbitals, which all have combined T1U symmetry available for bonding. And so that we can see the energies right here are negative 120.7 electron volts for the s orbital and negative 11.7 electron volts for the p orbital. Or p orbitals, sorry. So in the case of the 6 fluorines that are going to be bound to that sulfur, we've previously determined that the sigma binding salx are going to have the symmetries of A1G, EG, and T1U. And in the case of the pi binding salx, the symmetries will be T1G, T2G, T1U, and T2U. And the energies for all 18 2p orbitals, or correction, 12 2p orbitals are going to be at negative 18.7 electron volts. So it lies within a good region to be able to bind both to the p orbitals and the s orbital on the sulfur. And so the first step to developing our MO diagram is that we want to look at what orbitals are going to be non-bonding, which are not going to have any interactions with the atoms in close proximity. And so we can see in the case of the s orbital, it has A1G symmetry. We're going to be forming an A1G molecular orbital with a 2p sigma salc. In the case of the 3p orbitals on the sulfur, they will have T1U symmetry. And so if we look at our symmetries for the salx on the fluorides, we can see that we're going to form both a sigma MO and also a pi MO in that case. And so that leaves us then with an EG set, a T2G set, a T1G, and a T2U set that are all going to be non-bonding. And so those are going to stay exactly at the same energy, and so we can just throw those in right here. And so we can see that those are going to stay at the same energy. They're going to be non-bonding. They're going to be completely inconsequential in the bonding setup of our molecule. So the next step will be to look at the bonding orbitals that are going to form, and the first ones we'll want to look at are the sigma bonding orbitals. So sigma bonding orbitals will always be much more energetically changed from their initial state. So because sigma orbitals have stronger overlaps, they're better overlaps, those interactions are going to form larger changes in energy. If we develop and look at what's going to happen in those cases, we'll see that the s orbital and the sigma orbital that has A1G are going to overlap with each other. They're pretty close, about 2 electron volts in proximity to each other. So we can see then that we're going to have an A1G bonding orbital that is going to be very low in energy. And then alternatively, we should then also have an anti-bonding orbital that also has a very large energy split. And so we can then draw now the anti-bonding orbital all the way up here. We can expect it to be a pretty strong interaction in that case. Right? And so next, what we can do is we can now look at what happens in the case of the T1U. So the T1U on the P is going to form both a sigma bond and a pi bonding molecular orbital in both of those cases. And so the sigma bonding orbital is going to be lower in energy because it's a sigma bond, and so we can expect it to be somewhere down here. And then we're also going to be forming then a T1U pi bond in that case. And so that energy split will be much less than the sigma bond. And so we can expect that to be a little bit below the energy of the non-bonding orbitals. Now, since we're drawing qualitative MO diagrams, we don't really have to necessarily worry and concern ourselves so much with, well, is this going to be above or below the energy of the s orbital? What is the exact distances between them going to be? Because we can't really determine that very well just based off of the information that we have. To get that, you would have to have a lot of spectroscopic information. You would probably also need to do a lot of, very computationally heavy work to be able to determine what exactly the energies are in each case and how that'll then change it. But based on what we're working with here, we can see that the sigma orbitals should have a very large split. Those should be much lower compared to the pi orbitals. The pi orbitals should be a little bit lower. And so then now finally, because you have to have the same number of molecular orbitals that you form as you have atomic orbitals that go into it, or salks, what we can see is that in the case of the anti-bonding orbital, that is now going to be higher in energy than the A1G, and I'm predicting that because in this case right here, this T1U molecular orbital that's going to be up here is not only going to have sigma anti-bonding character, but it will also have pi bond anti-bonding character. So it'll be both of those together in a single MO set, right? And so that's going to then push that further up. And so now we have our MO diagram right here, and so if we then go through and we add all of our electrons, what we'll see is that all of the electrons will fill up to the non-bonding orbital set right here, and so we'll have our HOMO-LUMO gap that'll be between the non-bonding orbitals and the sigma star orbital, the A1G orbital in this case right here.